So let's talk about what we've got going on in class. So we have um, we have an exam on Monday, and that starts at 7:45 a.m. in here. That's if you want that time. If you don't feel like you need, it's not going to be necessarily a longer exam. So like I said, I'm going to try to make it the same size exam as always in terms of time. This material has been a little challenging for folks, so maybe it'd be a little bit longer for you. But it's going to start at 7:45 a.m. in here if you want to come in that early. Runs to the normal 9:35. Okay, that was what's done with the other exams. Friday will be review. So you have the things we've covered. This is exam is everything from let's go ahead and talk about that. Polarity through Monday's lecture. And Monday's lecture was mostly review as well, but through solution stoichiometry. All right, so that's what it's going to be on. Everything since the last exam. There is a practice exam up with an answer key. That practice exam pretty much covers it as well in terms of the possible topics. Like I've said before, I made an effort, and I actually did a pretty good job this time. I would say 75% of the exam is problems directly out of the back of your book, odd number problems that you have the answers to. If you want to use those for practice, they're good practice. It's many chapters of practice for that, but if you want to use those are good practice. I'm available for help. Let's call them office hours. 1 to 5 p.m. We'll say today. It's Monday, Wednesday. I should be here for all of that. Let's say 3 to 3 p.m. not. Or 3 to 3:30 p.m. I'll be busy. I have a call I need to be on at that time. And then there's a help session on Thursday night at 7:30 for you guys on Google Meet. Questions on things we've got going on right now? Yes.
If we're taking an exam on Friday,
Let's talk about that. Come up, ask me afterwards. Okay. Other questions? All right. Then today is going to actually be new material, not on the exam. This material is important, but not on the exam. And this is because I pushed the exam back to Monday. This is important specifically. It's important overall in terms of a chemistry topic, but it's also specifically important for your lab when you get back. So Dr. Livingston, who's some of your lab instructors, said, hey, are you going to cover this before they get back from Thanksgiving break? So yes, I am. So think you could write down this is important for lab, and then we will pick it up and talk about it more after you get back. But what we're going to be talking about is energy. So this is about energy and heat. Okay, and when we talk about heat in chemistry, we use the term enthalpy. So heat equals enthalpy in chemistry. Physics as well. Okay, but we'll talk about that. So when we think about, we're going to start off by talking about some terminology related to these things. If we think about energy of, well, actually, let's before I say the word system, let me talk about system. So you can break the world up into, or the universe up into the system and the surroundings. All right. The system is kind of what you're manipulating, and heat can go in or out of it. Okay. Or energy really can go in or out of it, but we'll be focusing on heat. So the system is what you are manipulating or what you're working with. So this might be a reaction in a beaker. Okay. The surroundings is absolutely everything else. All right. And so energy can enter or leave the system. In particular, we're going to be talking about, so energy, when we think about energy leaving or entering the system, we talk about it as heat can enter or leave the system, but we also have this concept called entropy, which is a measure of disorder, and it is energy as well, okay? We're not going to talk about entropy today, and we're not going to talk about entropy for at least the day we be, a couple days probably. We're just going to really focus on heat for now. All right, but the energy is both of these things. So enthalpy, the heat isn't everything, is what I want to say. So for our purposes, our current purposes, we're going to focus on heat entering or leaving the system. All right, so then there's some sign conventions that happen in chemistry. So first off, what I want to talk to you about is this. You're going to see this a lot. Excuse me, or bless you. So delta H. H is enthalpy. Okay, and the delta is change. So the whole thing ends up being change in enthalpy. And so we'll be interested in a change in enthalpy for, mostly we're going to be talking about chemical reactions. We might talk about changes to a gas. We may start off with a little bit of changes in the gas. But let's say I have my system. So this is my system. And then everything else is surroundings. All right, everything else is surroundings. And if we have heat, I guess I should have done my system not in red. Heat can be blue. Hopefully it won't be confusing. If we have heat leave the system, all right, heat leaves what we're studying. What does that mean? What happened to the system? If heat leaves, what happens to the temperature of my system? It decreases, right? If it's just heat leaving and we don't have a chemical reaction going on. So you can think about so ice freezing. When ice freezes, heat is given off. Okay, the water gets colder and has to give up its heat to do that. That's an example of heat leaving the system. So that's a pretty obvious one, right? So let's say water turning to ice. That's heat leaving the system. Here's something that maybe isn't as obvious to you. I'm going to burn a piece of paper. Let's say the piece of paper is my system. The paper and the oxygen that's consumed in burning it. It's a combustion reaction. Okay, remember that for the test. But let's say burn a piece of paper. If the oxygen and the paper are the system, does heat leave? Yes, it's a little confusing based on this, right? It leaves because it gets hot. It's hot. You're standing next to it, you can feel heat. That's heat leaving. Okay? That is also a heat leaves the system. All right, does that make sense? So in both those cases, we're talking about that. The system is losing heat. So when we talk about, let me write that out. This is a convention, and you may just get used to it, but this is what the signs are, and that'll be fine. I was just used to it for a while. So heat leaves the system, so the enthalpy change is negative. Enthalpy is the amount of heat, and this is, we're talking about the change here, okay? It's negative, the system loses heat. That's why we have this system, or that's why these signs are going to be negative and positive for that. So you burn something, it's hot. That's a negative enthalpy change. Okay? This may seem a little bit abstract for the moment. We'll get into more of it, some of it today. But you will see this, is it negative, is it positive, over and over and over again in chemistry as you go forward. Okay? All right, so that says that if we add heat to a system, all right, so let's go ahead and we'll have our system again. This time I'll do my system as blue, and I'll do so I can have heat be red. My surroundings are out here. And so let's say we have heat goes into the system. So heat enters the system. What would be an example that isn't ice, doesn't involve ice, that would be with water, but with heat entering the system? Water boiling, exactly. You have to put what if you want to have water turning to a gas. Right? You know this. Oh, goodness. Let's see. Water turns to a gas. Okay? So you know this. When you put water, if you're going to turn water into gas on your stove, you put fire under it, right? You're adding heat to that system. All right, what was my other example up here? I burned a piece of paper. Okay, one of those chemical ice packs. All right, chemical ice pack. A chemical ice pack gets cold. Okay, that's also a heat enters the system. All right, so chemical ice pack, you break it, it gets cold, and it's sucking in heat. That's why it's cold. All right, to make the chemical change in that ice pack, and the chemical change is it's actually dissolving. So what goes on? We'll talk about this later. We'll talk about the dissolution, right? But there are some chemicals in there. You break. You've got water. You've got ammonium nitrate. Get familiar with ammonium nitrate. We'll get a fun story for that later. But ammonium nitrate dissolves into that water and it gets cold and it's sucking in heat in order to dissolve. That's what's going on. And if the cold bothers you here, if it was ice melting, that wouldn't be a problem, right? Ice melting, but the ice feels cold. It feels cold because it's sucking water out. It's sucking, as it melts, it's sucking heat out of your hand. Questions? And so in this case, so up here, I guess I didn't write it down. For this process up here, we would say that delta H, the change, is going to be less than 0. Heat is leaving the system. Or you might say that delta H is negative. Okay, and then down here, delta H, we've got heat entering the system. It's greater than 0, okay? Or delta H is positive.
So how is like the chemical ice pack getting cold not the same as water getting cold?
How is it not the same as water getting cold?
Yeah, like because you put water getting cold in the first one.
Where we talk about this,
Yeah.
water turning to ice. So if we think about the molecules, so at the molecular level, I can describe this at least. So you think about the molecules of the ice, right? So we've got water turning to ice, right? And so the molecules of water they're water, they're liquid, they're moving around. Actually, they're not moving around like that. They're moving around like this. Because water doesn't have space between the molecules, right? Or not much space. So rolling around each other, they have energy, and that for them to lock into place in terms of being ice, they have to lose energy, right? They have to stop moving, and so heat goes away. Okay. So for the chemical ice pack, a way of thinking about it is actually it's a pack. It's let's pretend the thing you're breaking has a solid pack in it. That might be easier to think about. It's actually a very concentrated solution. Let's pretend it's solid. Imagine it's solid. Those molecules are sitting like this, right? They're not moving around. And then you let them in, and then they start moving. So they grab, they need to pull energy, absorb energy to start moving around in solution. Does that help? Okay. I realize that I put up an example here, right? These examples don't seem to, this right here, these don't seem to exactly go together. It's a little non-intuitive, right? So if you think about what the molecules are doing, that helps. If you think about it as, two kinds of classes that are the same sort of thing, that may help too. So, okay. So we've got this, so we've got the big point here is we've talked about the heat leaving and entering, and we've got this delta H. Okay, that's our enthalpy, and that's whether it's leaving the system or not. So we also have this thing called specific heat. Okay, and essentially it is how much energy it takes to change the temperature of a substance. So we're still talking about here. So specific heat, and your book is using an S for this, so I will use an S. The specific heat is the amount of energy required to raise the amount of energy you have to put in to raise the temperature of 1 gram of substance 1 degree Celsius. Which is the same as 1 degree Kelvin, okay? Celsius degrees and Kelvin degrees are the same degrees, they're just shifted from one another, okay, the amount. Whereas for Fahrenheit, a Fahrenheit degree is smaller, right? There are more of them for a given amount of temperature, let's say. Okay, so and the units on this could change around. So you might see a problem where you'd have to get it into, it was in some other unit, you'd have to get it to grams, and you'd have to get it, well, not to Celsius, you could have to go from Fahrenheit to Celsius. I don't know if your book does that or not. That'd be kind of mean. I wouldn't bother to do it because you don't do Celsius in that, in science so much. So this is defined. So when we think about water, and so the amount of energy, actually, a couple different units we've got here. We're going to talk about a calorie. So this is like your dietary calorie, okay, but it's got a little, for chemistry, it has a little c. Your dietary calories also have little c's, right? So this is, a calorie is, let me go ahead and type it so it's easier to read. A calorie is equal to the amount of energy required to raise 1 gram of water 1 degree Celsius. Okay, this is related to your dietary calories. So this chemistry calorie, I'm going to write calorie like that. It's like this, and now I'm going to just put chemistry in front of it because you're used to calories from another term. A chemistry calorie, or let's say 1,000 chemistry calories, is equal to one dietary calorie. Okay, is equal to a calorie. So in chemistry, we're going to capitalize the C when we mean essentially a dietary calorie, 1,000 calories. Okay, if you see that. And in Europe, they don't talk about capital C calories. Actually, they talk about kilocalories, right? 1,000 little calories would be a kilocalorie. So if you go to Europe, you look at food, it's kilocalories in it, not calories. Questions on that unit? So that's 1 unit of heat, right? The amount of heat you have to put in to make that happen. Jude.
So wait, you said in Europe they have kilocalories, and that's like 1,000 of.
It's a kilocalorie is exactly our dietary calorie.
Okay, so
Right. So when you look at the back of their packaging, you'll see kilocalories instead of calories. Okay. So then I want to talk about one other energy unit that we will often use here, and that's called a joule. And a joule is based on, oh, I forget the physics terms. It's kilogram, Newton, it's a force and a mass and things like that. And I'll look it up and get it right next time we come back. But in chemistry, we don't really worry about the physics terms so much, except when we have to cancel units. But a joule is equal to 4.184 calories. Okay, but we use joules a lot too. And you've seen joules before. I think we did light, right? We converted it to energy. That was in joules. All right. Questions? Sorry, lots of definitions here. We're changing topics. All right, so we're talking about specific heat here. And so the specific heat, we can have an equation then. We have a specific heat is equal to the amount of heat, which is we're gonna use a little q for, times the mass times the change in temperature. Okay? Let's label what all these are. This is heat or enthalpy. This is specific heat. This is mass. Okay? And this is change in temperature. Should change in temperature be in Celsius or should it be in Kelvin? Kelvin is the safe answer, right? Put it in Kelvin, you're always safe. It doesn't matter. Let's take a look at that. So it doesn't matter because if we take, let's say, 0 degrees Celsius, right, is freezing and 37 is body temperature. So 37 degrees Celsius, we'll just figure out the difference between body temperature and ice freezing. Minus 0 degrees Celsius, right? So is equal to 37 degrees change, right? Celsius, that would be our change. So then let's do this in Kelvin. Kelvin, I'm going to add 273 to this, and I'm going to add 273 to this. Do you see that I've added the same amount to both of them? So when I subtract, it'll be the same. We'll do it anyway. But so 37 degrees Celsius plus 273 is 310 Kelvin minus 273. And that, if you put it in your calculators, is going to give you 37 degrees Kelvin for our change in temperature. So because it's a change in temperature, and because Celsius and Kelvin have the same size degrees, a degree Kelvin and a degree Celsius are the same size, it doesn't matter when you're doing a change. So you won't have to worry about converting to Kelvin. All right, so we have this equation right here, and often we rearrange it. So what I'm going to do is I'm going to multiply both sides by mass times change in temperature. And what that's going to give me is let's go rearrange. But my rearrangement is just what I did there. And so I would end up with, if I keep it the same, things on the same side, it would look like this. But the way we'll usually express it is with the Q on the left-hand side. Okay, so this is if you want to figure out what the specific heat capacity was of, or specific heat, let me say capacity here, sorry. The specific heat capacity was of a substance, right? You could put a certain amount of heat in, if you could measure that, you could weigh it on a balance, you could look at how much the temperature changed, and then you would know the specific heat. All right, I did not work out a problem ahead of time for this, so I'm going to make something up, and I'm not going to get the right specific heat capacity for iron, okay? But I'm going to try. I'll try to get close. I actually don't even remember it exactly. But let's say a piece of iron let's try this. Let's say 41.2 calories of heat are added to a, let's go with a 4.00 gram piece of iron. All right, so 41.2 calories of each piece of iron. The temperature of the iron, yeah, I'll go with that one. Temperature of the iron raises by 1.1 degrees Celsius. What is the specific heat capacity of the iron? Okay, this is one of these things. Whenever you're using this equation, you're going to be given, we've got 1, 2, 3, 4 variables in this. Okay, well, the specific heat capacity isn't a variable. It's constant for a substance. You could look it up, but we might be solving for it. So you've got 4 things in this, and you're going to be either given 3 or a way to figure out 3, and then you'll solve for the 4th one. And if I've written this correctly, I've done that. It looks like I have. So then what we're going to do is I've got 4 grams of iron. That's my mass. I have 41 calories of heat that are added. My change in temperature, so this might have been given to me as, you know, the temperature goes from 23 degrees Celsius to 24.1 degrees Celsius, right? And then you'd be able to figure that out. And then just by the difference of the two. And then I'm going to solve for S, the specific heat capacity of iron. And so I'm going to go ahead and put these numbers in. So if I go ahead and I put 1.1 degrees Celsius, and my mass is going to be 4.00 grams, and my specific heat capacity I'm solving for, and my heat is 41.2 calories, which you can abbreviate as lowercase cal. All right. To solve this, I need to get specific heat capacity by itself. How would I do that? I can divide by, I can divide by 4.00 grams on this side, right? And I can also divide by what on this side? 1.1 degrees Celsius. And if I do anything to one side of the equation, I have to do it to the other side of the equation. Like that. These cancel, and I'm left with specific heat capacity is equal to 41.2 degrees Celsius over, no calories, I'm sorry. Divided by 4.00 grams times 1.1 degrees Celsius, right? Put that into your calculator, and you're going to get something like a tenth, because that's what I was aiming for. You guys can look up what the heat capacity of iron is, but I have in my head it's about a tenth of that of water. So 41.2 divided by 4 divided by 1.1. And I'm pressing the divide sign before everything on the bottom. So I put this in my calculator. I put that number in, I divide by divide, and I divide again. And that's the way you can use your calculator. We've talked about that before. That's the way you can use your calculator quickly. And no, I did it wrong, I guess. No, I didn't do it wrong. This is 9.36. Yeah, I did it wrong. That's not iron, but anyway. All right, so what are my units here, though? I didn't do the problem wrong. I just made it up wrong. So it's an unrealistic value. Calories per gram degrees Celsius. I pulled them straight out of over here. Okay? That's the really cool thing about keeping your units along. When you have to give your units at the end, right, to get full credit on the problem, you can pull them directly out of the problem if you canceled carefully. Right. So I'm going to just say right here, not really iron. All right, so I forgot to look this up. Let's go ahead and look up the specific heat capacity of iron on the interwebs. Thank you, AI overview. Okay, so for calories, you're not going to give it to me in calories. Joules is really a better unit of measurement, but all right, so it's 0.449, so joules per gram Celsius. We'll just convert that real quick. I'd like to work in calories because it's just easier to think about because water is 1, right? It's always nice when you have water as a base of 1 for these things. Okay. So iron would be, we had 0.449, what was it, joule joules per, I'm going to do this with dimensional analysis, so we had some units on the bottom, joules per gram degree Celsius, right? And we know from up above that 4.184 joules is equal to a calorie. And so if I have 4.184 joules, I will have 1 calorie. 0.449 divided by 0.449 divided by 4.184. And so I get 0.11 really. How many sig figs do I have? 3. 0.107 0.107 joules, right? Joules going to cancel here, or it's going to be calories. Calories per gram degree Celsius. Okay. So what does this mean? This is iron. Okay. So that's iron. So what does that mean? Is it easier or harder to heat a quantity of iron up than a quantity of water? It is easier to heat the quantity of iron up. So you can get your iron, your cast iron pan that you put on the stove. I'm a big fan of my cast iron pan for certain things. Okay, but your cast iron pan you put on your stove, it's much easier to heat that up than the water. If you filled your cast iron pan up with water, the same mass of water, let's say. So since iron's heavier, let's say I had to fill it up. It'd be easier to get that cast iron pan blazing hot than it would be to heat up water. Does that make sense? And it should actually, if you've cooked, it should make some sense there. Because if I take my pan, I mean, have your parents ever harped on you by sticking the pan on the stove and turning the heat on before you put the stuff in? Yeah, I mean, we harp on our kids about that all the time because that pan can just get enormously hot before you actually get the food into it. And you want to get there's a lot, most of your recipes will say, put the oil in, heat it up, drop your food in. That's fine. But the walking away and looking at your iPad while the pan's on the stove is not a good thing. Maybe you never do that. So this iron heats up a lot faster. Okay? And as we talk about heat, we won't go into it in detail today, but a lot of cooking food, a lot of the concepts of cooking, a lot of things you do have to do with the fact that it takes a lot of energy to heat up water. Okay? And it takes even more energy to turn it into a gas. And it's really cool stuff in this chapter. But we're not going to cover it today. We'll cover it after you've taken your exam when you'll remember it better. Okay. So we're working up to these concepts you need for lab, though, right? You are going to go into lab and you are going to measure. I didn't read it exactly. You're going to do calorimetry. So you're going to measure the specific heat capacity, something, or you're going to measure how much heat's given off. We're giving you all the tools for those sorts of things today. All right. So we have this thing called specific heat capacity, which is about how much per gram, how many calories per gram it takes to heat something up, right? Really down here for iron. Now, if I know that, now I have my heat capacity for iron there, right? Okay, so now I can do a really cool experiment. So I know from this equation, from this rearrangement right here, we've got that, right? If I take, let's say I've got a tub of water and it's insulated. So my system is this tub of water. And that tub of water is at some temperature. Okay. And I'm just going to say some temperature before I write it. We'll replace this. But got that at some temperature. And I take a hot piece of iron and I drop it in there. What's going to happen? So the water is at, let's say I'm just going to make these numbers up and we'll make it no problem in a second. But I want to show you the equation in a second first. So let's say the iron's at 90 degrees Celsius. Let's not make it boil because that'll make things more complicated. But it's at 90 degrees Celsius and the water's at room temperature, so 21 degrees Celsius. Okay? Which way is the heat going to move? Heat is energy. Is the heat going to move into the iron or out of the iron? Out of the iron. The iron's hot, it's going to cool down, right? So if this is 60 degrees Celsius, this is going to end up being our problem. And this is 21 degrees Celsius. Heat, temperature. Temperature is it's a measure of the average motion of molecules, the average energy of molecules for us. Okay, that's what it does for us. And really, technically, the only thing it's really specifically good for, when we're just talking about straight out temperature, is what direction. It tells us what direction heat will flow. Heat will always flow from higher temperature to lower temperature. Let's say that one. Heat will always flow from higher temperature to lower temperature. All right, and so what that means here is when we put this hot piece of iron in here, we'll make this iron, we'll make this water, okay, that heat flows out. Okay, and so what that means is that our iron will cool. Fe cools, H2O heats. Okay, in other words, the temperature goes up for the water. But the amount of water, the amount of heat that flows out of the iron is going to be equal to the amount of heat absorbed by the water. Does that make sense? That those would be equal? So we can describe the heat leaving the iron by this equation, right? The heat leaving the iron is the heat that's released by the iron. That's going to be equal to the specific heat capacity of the iron times the mass of the iron times the change in temperature of the iron, right? And the heat entering, the water, the heat entering the water is going to be equal to the specific heat capacity of the water times the mass of the water times the change in temperature of the water. Okay, but this is equal to this, right? All the heat that comes out of the iron is equal to this, except the sign changes, because this, if we talk about the iron, this loses heat, right? So the sign here would be negative or positive. It loses heat, so this is negative. It gains heat, so this is positive. All right. And so I can rewrite, since these are equal except for a difference in sign, I can rewrite this process, and then I can solve cool problems. So I've got my temperature, my specific heat capacity of my iron times my mass of my iron times my change in temperature of my iron is going to be equal to, I can make this negative, okay? I'll make it negative for a moment, is equal to the times the specific heat capacity of my water times the mass of my water times the change in temperature of my water. Okay? Does that make sense? Those two are equal, the amount of heat being transferred. Do you see that if, it doesn't really matter where I put this negative sign, we made the negative sign go with the way the heat was flowing, okay? But it doesn't matter because if I multiply this equation by -1, what happens? This negative goes away right here, right? And this negative goes right there. So don't stress about where the negative sign goes, just make sure you have it on one side, some side, okay? And the rest, it'll all work out. All right, so let's say for the system above, so we've got parts of that, right? Let's go ahead and write this out as a problem. So a piece of iron at 60 degrees Celsius is added to 100 grams of water at 21 degrees Celsius. Okay? If the starting temperature of the iron, I'm sorry, we need the mass of the iron. If the mass of the iron, we have the starting temperatures. If the mass of the iron is, I don't know, let's make it 45 grams, and the ending temperature of the water and the iron, they come to equilibrium, they get to be the same temperature. The ending temperature of the water and the iron is, let's say, 23 degrees Celsius. I think I did the whole problem. I gave you all the things, didn't I? What is the specific heat capacity of the iron? I'm going to say metal. I'm going to change my problem to say metal, because I accidentally gave us all the parameters there. We need to solve for something. All right, so we're going to change this problem around just slightly. And up here, we're going to change this to be metal. All right, well, this is our equation we're going to use to solve this. All right, we've got it right here. Okay, and so we've got various things we can put in here. But the first thing, though, is we need to get what these change in temperatures are. Right, we don't know what these change in temperatures are. They're not given to us. So we have our metal, change in temperature for our metal. Our metal starts at what? 60 degrees Celsius, and it becomes 23 degrees Celsius. So our difference there is 37. Check my math. Okay. Our change in temperature for our water is going to be, it starts at 21 degrees Celsius, and it ends up at 23 degrees Celsius. So that's going to be -2 degrees Celsius. Okay? The sign is important here because we have that negative sign up above. That's where that negative sign up above comes in. Did I get the first one right in terms of the 37 off the top of my head? All right, great. All right, so now we're ready. We have everything we need to put in here. So let's see. These should be metal instead of iron up here. Metal, metal, metal. And so what I'm going to do is now I've got the change in temperature for my metal goes there, right? The mass of my metal is 45 grams, goes there. I'm solving for the specific heat capacity of my metal. I know that the specific heat capacity of water is 1, right? From up above, or I'll just look it up on my constants sheet. So I'm going to know this. I know I have 100 grams of water, and I know my change in temperature for water is this. So you see, I have this equation. It has 6 things in it, and we only have one we don't know. So we can solve for it. So let's go ahead and write all those numbers in, and then I've got one more important equation to show you before we're done today. I'm going to go ahead and the mass of the iron, so I've got the specific heat capacity of the metal is equal to times 45 grams, right? Times the change in temperature that we said was 37 degrees Celsius is equal to negative times the heat capacity of water, which is 1 calorie per gram degree Celsius, times the mass of the water, which was 100 grams, okay, times the change in temperature of the water, which was negative 2 degrees Celsius. Don't lose the sign. Do you see I have a negative on this side and another negative? I can, negative 1 times negative 1, I can cancel my negatives. So I'm going to do that. And then I'm going to divide both sides by what's over here. So I'm just going to put the numbers down here for the moment, and I'll carry the units over to the other side. Okay, these all cancel, and that's going to make a 1. No, I'm doing it wrong. You guys should have jumped in there. Maybe somebody had their hand up. I've got to solve for my specific heat capacity, right? So I've got to divide 45 grams times 37 degrees Celsius over here. These cancel. And then I'm going to put 45 grams and 37 degrees Celsius over here. Celsius cancels with Celsius, grams cancel with grams, and my units are going to be units for a specific heat capacity. Fantastic. That tells me that I probably did the problem correctly, which is, if I'd done it the other way, I wouldn't have. And so I'm going to multiply across the top 1 times 100 times 2 divided by 45 divided by 37. And I get a heat capacity of 1.012. The specific heat capacity of my metal is 0.12. That's too many significant figures, but I'm going to keep them anyway. I guess I won't keep them. I'll do it right. I only gave you one significant figure on the grams of the metal, or the grams of the water, so that my answer would be that many calories per gram degree Celsius, which actually is pretty close to iron. Questions? How we would use this arrangement of equations right here. So that's the important thing. How do I use this for a problem where I'm heat transferring from one thing to another? Okay. So then I want to introduce one more. So you're going to be doing in lab something called calorimetry. And calorimetry is the measure of heats in chemistry. We measure and study of heat or enthalpy. Let's say heat. So you're going to make yourself a little calorimeter, and you're going to drop something in it or run a reaction in it or something, and you're going to use it. The calorimeter is going to be like, I'm not sure what they're going to have used, but it's probably a styrofoam cup and water with a cap on it and a thermometer. And so you run a reaction in it, or you drop a metal in it or something, and you study how much the water changes temperature, and the water will either absorb or give off an amount of heat related to how much is absorbed or given off by the reaction. Does that make sense? Just like for this piece of iron. But you could be doing a reaction like what happens when you have one of those chemical cold packs. You break it and heat is absorbed and the water temperature goes down. Okay, so that's what's going to happen. But instead, for your calorimeter, what you're going to do is you're going to have, this is going to be the equation for the calorimeter. Okay, and so what you do for a calorimeter is you're going to have a heat capacity, not a specific heat capacity times temperature. Your calorimeter is an object, it's a cup, and it has water in it, and there's a thermometer sitting in it, right? It's a mixture of a bunch of different elements and substances. And so you don't really talk about what the specific heat capacity is of each times the mass. This has for your calorimeter, this heat capacity. And it has your specific heat capacity and mass. I'm going to say specific heat capacities and masses built in. Okay? So it is, in terms of that cup, it is the heat capacity of your water times the grams of your water, plus the heat capacity of the thermometer and the grams of thermometer, plus the heat capacity of whatever amount of the outside of that styrofoam cup is actually interacting, right? It's mostly insulating, times the mass of that. Okay? So we're just mashing all of that into one term. So if you remember, which you may not because this is probably pretty abstract to you at the moment, right? That's our equation, and essentially what we've done is we've taken this bit of it and we've replaced it with that. Yes?
What's the word under heat?
Masses. Sorry, my pen was failing there. My writing is not quite that bad, although it's pretty close. Okay. So what you're going to do in lab is you're going to have a calorimeter, right? And you're going to run some sort of reaction. You're going to calibrate your calorimeter. You're going to run something, you know exactly how much heat it gives off, and then that's going to give you your units for your calorimeter. Okay? So it gives off, you know how much heat, you watch how much your calorimeter changes in temperature, now your calorimeter is calibrated. And then you can measure things using your calorimeter. Let's very quickly, in 1 minute, kind of try a reaction. A reaction releases, let's say, 350. No, that's too much. It releases, we'll do 35 calories of heat into a calorimeter. I still have a minute. The temperature of the calorimeter raises by, let's say, I don't know, 3 degrees. Okay, what is the heat capacity of the calorimeter? All right, so we've got this equation up here. What we would do here, I know you guys are really chomping at the bit to get out of here, so I'm going to go, this goes here, this goes here, and you solve for C. All right, and so C is going to be about 10. Okay, and the units come just straight out of this. Heat is going to be in calories, and temperature is going to be in degrees Celsius, right? So it's going to be the units on this. The units are going to be calories per degree Celsius. All right. Yes.
Are you going to post this on the YouTube channel?
I will post this. Yes. And you're welcome to ask questions and any of the help sessions as well. Okay, you guys may go.